Hey there, fellow mathematicians. Welcome to episode 13 of Math 141 Recitation, Summer 2020. Today we are going to be talking about concavities, when functions eat too much candy. Do you get the joke? The joke is like if people eat too much candy, then they get a cavity. Get it? Ha ha ha, concavity, ha. In particular, we are going to be doing problems from the 4.4 homework, which covers concavity and curve sketching. This is a really neat chapter. I think that I've said that about just about every chapter. But this chapter is very neat because we start to see how we can use the first and second derivatives and some of the ideas which we've been developing in order to get a rough idea of a graph without actually knowing what the function is. Just from its derivatives, we can go ahead and start to gain some pretty cool information. So not a ton of problems on this homework assignment, but that's because these problems are quite involved and have a lot going on. So lots of pieces where we're going to really start putting some stuff together. So I can't wait. I know that you can't wait either. So let's stop wasting time. The first problem which I would like to do from this homework set is problem 4. And here we are going to find the coordinates of any local extreme points of any local extreme points. You may also see that written as local extrema. That's how I was taught, but they mean the same thing. Extremum versus extreme point, they're the same. Any local extreme points and inflection points. So extreme points, that's what we were doing last time, right? That's like the maxes and mins of the functions. And then inflection points are where the concavity changes. Use these to graph the function. So here we're going to start to see how we can, in this case, we are going to be given the function. So we could graph it another way, but we'll start to see how we can use these pieces to give us a nice idea of what the graph looks like. Let me put this nice and bold down here. So this is y equals x minus sine of x. And we're only going to graph it over the interval on the interval 0 to 2 pi. 0 less than or equal to x less than or equal to 2 pi. That's perfectly fine because, well, actually x is going to change, but sine of x is going to be cyclic. So that's, I think, part of why they're focusing on this. So the first part asks us to find the coordinates of any local extreme points. So this doesn't officially break it up, but I'm going to go ahead and kind of do so. So first we're going to focus on extreme points. Okay, so as you'll recall from last time, what we want to do is we want to ask ourselves, where is y? Well, first of all, we want to find critical points. So find critical points. And in doing so, we're going to answer this question, which I was starting to ask, which means we're going to ask, where is y prime 0 or undefined? Well, let's go ahead and compute y prime. So y prime, let's see, the derivative of x, that is just 1. And then the derivative of sine of x is positive cosine of x, so that negative sign will remain a negative sign. So where is y prime 0 or undefined? Well, it doesn't look like it's undefined anywhere. So it's defined everywhere. Right? No matter what I plug in for x, this will give me a totally valid number. So it's defined everywhere, but I bet you it will be 0 somewhere. So let's see. So let us set 0. 0 equals 1 minus cosine of x. Well, that's the same as cosine of x equals 1. And let's see, we're in the interval. Okay, this is why they're restricting the interval. So we want to find all the points in the interval 0 to 2 pi where cosine of x is equal to 1. And that is going to be, if we draw our unit circle, that's going to be whenever we are at this point here, right? This point 1, 0. That's where cosine is 1. And this is the case at x equals 0 or 2 pi. Okay, so let me go back to this restriction of the interval for a second. Suppose that this interval was not restricted from 0 to 2 pi. Well, then we would also have these critical points at x equals 4 pi, x equals 6 pi, x equals negative 2 pi, negative 4 pi. And so we'd have infinitely many critical points. Now, there's nothing wrong with that. We could do that, but it would certainly add another level of difficulty and abstraction. So keeping it within this range keeps things more manageable. Okay, so we've found our two critical points, our two critical x values. Those are x equals 0 and x equals 2 pi. Okay, so just like before, I'm going to draw a number line. Now this number line, I have a feeling we might want to come back to later. So I'm going to make it nice and big and give us plenty of room. Okay, plenty of room above and below it. The points which I will label, well, we're only interested in the interval from 0 to 2 pi. So I'll go ahead and just put those at the end. We might need more points later, we'll see. But for now, this will certainly do. So we want to know what the heck is happening at these points. Well, what is happening to the derivative on the inside, right? We want to know, remember, what f prime is doing, what f prime of x is doing in the middle here, to the right of 0 and to the left of 2 pi. So y prime, I can plug in any point here, right? So let's go ahead and just check it at pi. So y prime of pi, because that's right in the middle, sure. So y prime is 1 minus cosine of x. So let me see, y prime of pi equals 1 minus cosine of pi. So that's going to be 1 minus negative 1, and that's going to be 2. So that means that the derivative is positive. So y prime is positive over this interval. Okay, so let me write it. Let me instead write this. I'll just write it like this: y prime greater than 0. Okay, so y prime is greater than 0 over this interval 0 to 2 pi. So over 0 to pi. So this tells me that we have a global min, at x equals 0. Okay, the reason that we have a global min there at x equals 0, well, everywhere else, whenever I move to the right of 0, we're just getting bigger. The function is getting bigger because the derivative is positive. And since our function is restricted to the domain 0 to 2 pi in this case, it certainly isn't going to get any smaller than all the way at the left. So at x equals 0, this gives us a global min of, let's just plug in 0 into our function. Our function was y equals x minus sine x. So I plug in x equals 0, and I get 0 minus sine of 0. That's 0 minus 0, and that is just 0. So global min is 0, 0. Similarly, we also have a global max at x equals 2 pi. Again, we see that the function is increasing because y prime is greater than 0 over this interval from 0 to 2 pi. Okay, which means that the function is increasing the whole way, so it's going to obtain its maximum all the way at the right, which in this case is x equals 2 pi. So if we go ahead and plug that into our function, global min, the x is 2 pi. The y, if I go and look at my function, y equals 2 pi minus sine of 2 pi. Well, sine of 2 pi, that's 0. So this is just 2 pi, 2 pi. All right? So we have found our global max. Excuse me, well, both. We found our global max and our global min. I'm seeing that I wrote this wrong. That should say global max. Do what I say, not what I do. Okay. Great. Now, we don't have any local extreme points aside from these two, right? Sometimes we can have local extrema, but not global extrema. But in this case, there are no other extrema because the only critical points are the endpoints. So that brings us to the second part now. We have found, so let me go to the start here. Find the coordinates of any local extreme points. Just did that. So next up are the inflection points. Okay. So I should have written that. You know what? I'm just going to make a new number line here whenever we need it. Inflection points. And so, as I hope you recall from Mackenzie's video or the textbook or whatever source, what we need to do in this case is we're basically going to do the same thing as what we've done to find these extrema, except we're going to do it with y double prime. Okay, so we need to take the derivative of our derivative. So y double prime, let's go and look at y prime. So y prime was 1 minus cosine of x. So whenever I take the derivative of that, well, the 1, that's a derivative has 0. And then the derivative of cosine is negative sine. So since I already have a negative sign out front, right, I've got negative sine. So that's just going to be y double prime equals sine of x. Okay, so now the question is again, just as before, where is y double prime 0 or undefined? Well, just like the first derivative, no matter what I plug into y double prime for x, I'll get something that makes sense, right? So certainly this isn't undefined anywhere. In other words, it is defined everywhere. So defined everywhere. Okay. So we just need to find where it's equal to 0. So just as before, let us, oh, I can't decide what color. Let's go back to black. 0 equals sine of x. Again, we are restricted to the domain 0 to 2 pi. So the only place where sine of x is 0 on that interval, I almost messed this up. So this is the same as saying x equals, it could be 0, it could be 2 pi. I almost forgot about 1. Or it could be 1 pi, just regular old pi. Life of pi. Okay. So just as before, yeah, I should have made that first number line simpler because I should have known I was just going to make another one because it's just easier. So just like before, let me make oh boy, what is going on? Let's make a number line, 0 pi, 2 pi. And now we want to check the concavity on each of these intervals. So rather than plugging stuff in, so we're going to do basically the exact same procedure. So we're going to plug in a point from each of these intervals, so from 0 to pi, and then from pi to 2 pi. We're going to plug in a value into y double prime and see what the concavity is. So let's first plug in, I don't know, pi over 2, I suppose. That's a nice value right between 0 and pi. So y double prime of pi over 2, Well, y double prime is just sine. So this is equals sine of pi over 2. Sine of pi over 2, we're all unit circle experts. That's 1, which is certainly greater than 0. So the way that I'm going to write this, you can write it however you want. This is just how my calculus teacher wrote it. I'm just going to write concave up, CCU, between 0 and pi to help me remember that. Okay. Now, similarly, we need to check something in the other interval from pi to 2 pi. So I'm going to go with 3 pi over 2. That is just sine of 3 pi over 2. And that is just -1. Which in this case, well, I almost said in this case is less than 0. Actually, that's always less than 0. I kind of glossed over this the first time, so let me emphasize here. Y double prime is positive at pi over 2, which means that it is concave up. The function is concave up between 0 and pi. And since y double prime is negative in the interval pi to 2 pi, that means that the function is concave down on that interval. Okay. Now, these things can be tough to sketch and kind of tough to visualize. I know that completely. I had a hard time with that whenever I learned this stuff, but let's go ahead and give it our best bet, because let me see, I'm pretty sure that we... Okay, so to find the inflection points then, so we found where the concavity changes, so that's what an inflection point is. An inflection point is where the concavity changes, where concavity changes. In this case, we see that at x equals pi, the concavity changes from being concave up to all of a sudden being concave down. So at x equals pi, we will have an inflection point, an inflection point. Now, I should note, if we got concave up and again concave up, then pi would not be an inflection point. Okay, the concavity must change. Okay, so that's an important thing to highlight. In this case, x equals pi. So let me emphasize where concavity changes, not just where the second derivative is 0. So x equals pi, so let's just plug that into our function to find the y coordinate. So y then equals pi minus sine of pi. Well, sine of pi is 0, so that is just pi. So pi is, in this case, our lone inflection point. All right, so we have found our inflection points. Check. So all that's left to do is to use the information which we have gathered to graph the function. So let's go ahead and sketch the plane. I'm going to just, why don't we do this? I'm going to start it at x equals 0. There's no reason to go any further to the left in this case. 2 pi is here, 0 is here. Okay. So let's first go and find a few points and find these important. We've kind of highlighted a few important points here. The first one, we know the point pi, so that's going to be important. So let's, I don't know, maybe this is pi. And maybe trying to go equally distant, maybe here or so is also pi on the y-axis. So this point here, that's going to be our inflection point. Okay, so that's going to be an important point later on. What other points did we emphasize? We also emphasized that there was a global max at 2 pi. Okay, so let me go ahead and map 2 pi. So 2 pi is maybe up here. We'll go up there maybe. 2 pi, so then we've got this point at 2 pi, right about there. So that is our global max. And then, of course, we have our global min down here at 0, 0. Okay? So this is a starting point. And before today, we wouldn't really have much more to go off of, right? In fact, we would say, oh, this is probably a line. It looks like a line would go straight through these, right? It looks like a line would connect these things. But we know that on the interval, now we know from the interval 0 to pi, the function is concave up. So from 0 to pi, the function will look something like this. So concave up, the way that I remember it, concave up, it kind of looks like, it sounds and looks, if you write it like this way, it looks like cup, concave up, cup, 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 cup. And in it, I don't know, and it looks kind of like a cup, like it looks like you could pour something into it, right? I mean, it's going to look something like this-ish, which means that, yeah, you know, I can pour my non-alcoholic beverage right in here. I don't know if that's going to be helpful for you. That's helpful for me. That's how I think about it. I need silly tricks like that to help me remember things. And then concave down is kind of just the opposite, right? The opposite. It's more going down-ish. So as we go here now to our graph, it's going to look something more like this. Something like that, maybe. Again, we still don't have all of the information, right? Technically, we would need to know a little bit more information to 100% accurately graph the function. But from just these few pieces of information, we can gain a pretty nice estimate. Okay, so that's the graph that we're going to go with. That's about what we have at this point. Okay, so I believe that does it for that first problem. Quite a doozy. Not terribly difficult, right? It's certainly tricky, but you know, it took us 20 minutes to do it, not because, oh my God, this is so hard. It is tricky, but it's definitely doable and manageable. It's really just putting together a lot of little things. The next problem I want to do is problem 5. It's looking like we may only have time for 3 problems, and that's okay. I adjusted today and only picked out 4 that I wanted to do rather than what I've been doing. So if we only get through 3, that is okay. Find and graph the coordinates is basically going to be the same instructions with a different function, which I think is plenty good practice for this new skill of any local extreme points and inflection points. Inflection points of the function let's see the function. Okay, let me make this nice and clear again. I should have used a different color, but that's okay. Y equals x squared minus 5 over x minus 3, and this is also an important detail. X is not equal to 3. Okay? Notice that that's important because if x was equal to 3, then we would be dividing by 3 and all chaos would break loose. Okay, so this time, let's jump in. And again, the first thing which I want to focus on are the local extreme points. Okay. So let's first find the critical points. So find critical points, which again, where is y prime equal to 0 or undefined? In this case, I think we are going to have a place where it's undefined. So let's go ahead and compute y prime. Well, we're going to have to use the quotient rule. Okay. So y prime, I'm not going to spend a ton of time on it here, just because we have plenty of things to worry about in this video. So let me see. First, I'm going to, in the numerator, differentiate the numerator, then multiply by the denominator. Then I will subtract. Let me see. I'm going to leave the numerator alone this time and multiply by the derivative of the denominator. And then I'm going to put this all over that denominator squared. Now let's see what simplification we can do here. Let's see, I get 2x squared minus 6x minus x squared plus 5 all over x minus 3 quantity squared. Let me do a bit of simplification up there. X squared minus 6x plus 5 over x minus 3 squared. In that numerator, this will be helpful in just a moment, that numerator is just x minus 5, x minus 1. And let me write y double prime here again, or y prime, just to clarify. All right, so we found our first derivative. And so the question becomes, where is this undefined and where is this 0? Well, y prime is y prime is undefined at x equals 3. Now it's worth noting that y itself is also undefined at x equals 3. So we can't have a maximum there. But it's still worth looking at to see what's going on with the function. So note, y is undefined at x equals 3 as well. Okay, so this means we can't have a max or min there, because in order to have a max or min there, we would need to have the function be defined there. So no max or min at x equals 3. Let's set this thing equal to 0. 0 equals x minus 5, x minus 1 over x minus 3 quantity squared. Well, now I'm just going to multiply both sides by that denominator, and I get 0 equals x minus 5, x minus 1. And now, this is why that factoring was super nice. Now we can nice and easily see that this means that x equals 5 or x equals 1. So this gives us our critical points. So we have these critical points, and x equals 3 is our, was that it? Yeah, 3. These are all of our critical points. Okay. Remember, the critical points are where the derivative is undefined or 0. So that's why x equals 3 is also a critical point. So let's make our number line, and we want to label 1, 3, and 5. So 1, 3, and 5. Now our function here, let's see, our function is defined for all real numbers. So we don't have endpoints, all real numbers except for 3, excuse me. So we don't have endpoints that we need to check. Remember, we usually need to check endpoints for maximums and minimums. But here we have no endpoints, so we don't need to check the endpoints. However, we are going to have to check these intervals on the end. Right, we're going to check, let me go ahead and sketch out our intervals again. From negative infinity to 1, from 1 to 3, 3 to 5, and 5 to infinity. Now I might go through these computations a little bit quickly. The point is we're going to do exactly what we've done before. So I'm going to plug in a point to the left of, that's a positive 1. So I'm going to use the point 0. Okay, so we're going to plug in a point to the left of 1. And let me see, y prime is x minus 5, x minus 1 over x minus 3 squared. So that's going to be 0 minus 5, 0 minus 1, all over 0 minus 3 squared. And that is negative 5, negative 1 over 9. And that is greater than 0. That numerator is just 5, right? And the denominator is 9. So it's positive here. The derivative is positive there. Y prime of 3 now is going to be, excuse me, not y prime of 3, y prime of something in between 1 and 3. Let's go y prime of 2. So that's going to be 2 minus 5, 2 minus 1, all over 2 minus 3 quantity squared. And that gives me a negative 3, a positive 1 over a positive 1. And that is negative 3, which is smaller than 0. So we put a negative between 1 and 3. Sorry, I thought I heard some sort of like knocking or banging. It's just the ghost, I'm sure. Y prime of 4, so now I'm going to plug in something between 3 and 5. 4 minus 5, 4 minus 1 over 4 minus 3 squared. Let's see, that's going to be negative 1, positive 3 over positive 1. And that is going to be less than 0. So we're negative here as well. And then 5, y prime of 5 equals, again, oh no, I did that thing again. I don't want to pick 5. I want to pick something bigger than 5. I'll pick 6. 6 minus 5, 6 minus 1 over 6 minus 3 quantity squared. And I'm just going to go ahead and assert that that is positive because everything in sight here is positive. So, looking at this information now, I can see that I have a local min at x equals 1. Okay. In fact, let me think about it actually. Why don't we instead, so instead of doing this the old-fashioned way, no, actually, never mind. We'll go ahead and do it the old-fashioned way. I was going to say we could also potentially use the second derivative test. Yeah, actually, why don't we go ahead and do that instead? Now that I think about it. No, we'll do that for, sorry. We'll do that for the next one. For now, we've already gotten all this information. So let's just go ahead and see what's going on here. It looks like we have a local min, or is it a max? Excuse me, local max at x equals 1 because the derivative is increasing and then decreasing. Excuse me, the derivative is positive and then negative. So the function is increasing before 1 and then decreasing after 1. So local max at x equals 1, and in fact, this is the point. 1, well, let's plug 1 into our original function to find the y-coordinate. So that's going to be negative 4 on top, negative 2 on the bottom, so that's going to be 2. So local max at 1, 2. What other extrema do we see here? Well, at 3, we don't see an extremum, right? That was that funny point where the function is undefined. But even if it were defined there, we wouldn't have an extremum because the derivative is negative both to the left and to the right of it. We do have, however, a minimum, a local min at x equals 5. So a local min at x equals 5. And this is 5. Let's go ahead and plug that into our function 5 squared minus 5, so that's going to be 20 over 2 is going to be 10, I believe. 5, 10, is that right? Hang on a minute. Something is fishy here. Because 5 squared minus 5, that is 20. 5 minus 3, something isn't right here. Let me look at y prime x minus 5, x minus 1, negative. So what I'm curious about, oh, okay. I see. Okay, this is very interesting. Okay, so this is right, what we're saying. Everything is good here. What I was concerned about was that supposedly we have this local max at x equals 1, and our y value is 2. But then here at 5, we have a local min, and the y value is 10, which doesn't make sense because we've got these negative values, right? We've got these negative derivatives, which means that the function is decreasing. However, this is possible. So this is possible because of this hole at x equals 3. Because of the hole at x equals 3. It's possible, and this is not necessarily our graph, but just to show you that this kind of behavior is possible. It's possible that our function looks something like this. So it might look like this. Okay, and this is x equals 1 here. Or no, hang on. Where this is x equals 1. Right, so I know this isn't the point 1, 2, but the point is we have this local max here. Right, we have this local max here at x equals 1. And then we have this hole at x equals 3. Right, so the function is undefined. And then it goes like this. Just to the right of that hole, it starts out huge. It is possible then for the function, you can see the function is decreasing, right? It's decreasing over the intervals we've said it was. And yet we still have this local min. In fact, let me draw that a little better. It could look something like that, yeah. But we still have this local min here at x equals 5. Again, this is a very rough sketch. But we still have this local min is bigger than the local max. So the point of all this, again, I don't know if this is the correct graph. We're going to get some more information to find out. But it's certainly possible. However, I do encourage you, those are the kinds of things that as you're going about this, you might want to stop and say, wait a minute, does that make any sense? And thankfully, in this case, it does. Okay, so we found these local extrema. If we wanted to look for absolute extrema, we could potentially take limits, but the problem doesn't ask for it, so I don't think we're going to worry about it here. So if we go back up to what the problem is asking for, what it is asking for, we found the local extreme points, check. So now we need to find the inflection points. So again, inflection points. And just like before, we want to look at f double prime, or I suppose I should say y double prime. Okay, so y double prime equals, okay, let's find y prime. Y prime, okay, so I'm going to use, let me think. Okay, so hang on a minute. I'm going to rewrite y prime as x squared minus 6x plus 5 over, I want to multiply that denominator out, x squared minus 6x plus 9. Because I think that will be helpful for me in taking this second derivative. Okay, so again, I'm going to have to use the quotient rule. I might go through this kind of quickly again because at this point, hopefully computing derivatives isn't too terrible. So if I take the derivative of the numerator, I get 2x minus 6. So this is 2x minus 6. And now I'm going to leave that as that denominator as x minus 3 squared here. So minus x squared minus 6x plus 5. And here I'm going to leave that as x minus 5, x minus 1. And then I'm going to multiply that by the derivative of that denominator, which is 2x minus 6. And then this is all going to be over x minus 3 to the 4th. Okay. Let me see what simplification I can do. So I can pull out a 2x minus 6 up here. And multiply that all by x minus 3 squared minus, let's go ahead and multiply things out again to make things easier. So we can see if we can cancel some stuff. It's going to be x squared minus 6x minus 5 plus 5. Yeah, like that. All over, oh gosh, all over x minus 3 to the 4th. Okay, so now it's 2x minus 6. I'm just trying to simplify things to make them easier. Perhaps x squared minus 6x plus 9 minus x squared plus 6x minus 5. And I do think things are going to get easier here in just a minute. X minus 3 to the 4th. And then that's 2x minus 6. Because now look at this cancellation in these parentheses. I've got x squared's canceling and 6x is canceling. So this is just plus, so I've got plus 9 plus, yeah, I've got plus 9 and then, oh shoot, never mind, I shouldn't have put that parenthesis there. Yeah, plus 9 minus 5, so this is just 4 over x minus 3 to the 4th. Okay, so this becomes 8x. No, let's just leave it as it is. Okay, so this is y double prime. Fantastic. Very good. So, just like before, where is y double prime? Where is y double prime equal to 0 or undefined? Well, it's undefined. No, I don't want that random comma there. Undefined at x equals 3, just like before. And let's see, it is going to be 0 at x equals 3. To see that, no. Is that right? I think it is right. So the only point where it's equal to 0 would be if the numerator is 0. And the numerator is 0, yeah, if x equals 3. So excuse me, it's actually just, oh, wait a minute. Okay, so I can rewrite this derivative I'm seeing as 2 times x minus 3 times 4 over x minus 3 to the 4th. And this is 8 over x minus 3 cubed. Okay, so this is y double prime. So it's undefined at x equals 3. So we're still going to make our number line, but we're not going to have inflection points this time. Okay, so here is x equals 3. Let me see, so let me plug in, so just like before, let me do y double prime of 0. If I do y double prime of 0, well then my denominator is going to be negative, my numerator is positive. So concave down to the left because y double prime of 0, which is to the left of 3, is less than 0. Now, if I plug in, say, 5, y double prime of 5, well, then my numerator and denominator are both positive, so greater than 0. So we have, this is concave up here. Okay, so what I want to do now is I want to organize, this is kind of what I was thinking with the first problem. We have found that there are no inflection points. No inflection points. We would have an inflection point at x equals 3. However, remember, because y is undefined at y equals 3. At x equals 3. Okay. So what I want to do now is combine all of our information into one number line. We didn't have to do this the first time because it was a little bit simpler. But here, so let me see, I've got, what were our points here? 1, 3, and 5. So 1, 3, and 5. And I want to know f prime and concavity. Okay, so for example, this interval to the left, of x equals 1, well, there it's concave down. Let's go ahead and fill in this concavity part first. So it's concave down to the left of 3 and concave up to the right of 3. And now when we are to the left of 1, let me see, it goes plus, minus, minus, plus, okay? So plus, minus, minus, plus. Okay, so now we have kind of broken up our domain into these 4 intervals. So first we're going to label, this is x equals 1. Okay. This is x equals 3 and x equals 5. Okay, and you can see how we've kind of chopped this up into these intervals. So if I'm to the left of 1, well, first of all, let's find the y-coordinate at 1. I think we already did this. Yep, 1, 2. Okay, so point 1, and let's label, oh, I don't know, where would 2 be? Like here. 2, so this is the point 1, 2. Okay. We got this point 1, 2. That's going to be a local max. We have a local min at 5, 10. Oh boy, 10 is going to be way up here. I won't make it totally to scale, but I do want to make it a little bit higher. Okay, so 5, 10, we have this local max. Okay. And now we can chop up this interval and say, okay, well, to the left of this point 1, 2, the function is increasing and it's concave down. So that means that it looks something like that, maybe. Yeah, I would say that's concave down because it's not concave up. It doesn't look like a cup, right? If you tried to pour water or something here, it's just gonna like spill out to the left down here, right? So we got concave down here and increasing. Then I want to do concave down and decreasing. So something like, that's tough to draw, something like that maybe. And remember, we don't actually hit 3, so we've got kind of in this asymptote here. Let me go ahead and, right, we never actually hit x equals 3. Okay, now, so that covers these first 2 intervals. Now I'm looking at the interval from 3 to 5. We want to be concave up and we want to be decreasing. So we're going to be something like this. Okay, because it looks like a cup, but it's decreasing. And then we're going to be concave up and increasing, so we're going to be something like that. And I realize I ran into my number line a little bit, but I hope that you get the idea. Okay, so that does it for this problem. This is our sketched graph. And again, I hope you can see how cool it is. We can put all these pieces of information together to graph this picture. The way that you organize your information, for example, if you don't like this number line and table that I'm making, please find something that works for you. I will not be offended, and try something else. This is how I think about it, but if you would prefer to do something else, by all means, please do so. Find what works for you. So we'll do one more problem tonight. We don't have, just in the interest of time, I'm already at 50 minutes, I believe. So let's jump and do problem 7. I will say I have no problem not doing many problems, simply because most of these problems, if you understand these big picture ideas, you are in just fine shape to apply them to these other problems. The first derivative of a continuous function y equals f of x, function y equals f of x, is given. Okay, so notice in this problem, they're not going to tell us what the original function is. Okay, they're only going to tell us, I can't get that f, that bottom is bothering me, there we go. They are only telling us the first derivative of the function, and yet we're still going to be able to get a nice sense of the graph. And then sketch. So here they're going to give us even less information, and we're still going to be able to make a pretty nice picture. So it's a general shape of the graph of f, of the graph of f. Okay, so the derivative we are given, y prime equals 6 minus x squared. So let's start with the second derivative. Let's go ahead and compute that bad boy. I know we're going to need it. So y double prime, okay, well if we take this derivative of 6 is 0, derivative of x is 1, so that's just minus 1, and then it looks like I have minus 2x. So that gives us our second derivative. Now, just like before, it doesn't explicitly say that we want to compute the extrema. However, we do still want to find these points in order to help us sketch the picture. So let's make a note of that. So let's find the local extrema. Okay, so just like we have in the past, we want to find where y prime is, we want to find the critical points of this function. So find critical points y prime equals 0 or undefined. Well, y prime, as you can see at the top of the screen here, is 6 minus x squared. That's just a polynomial, so that is surely defined everywhere. So defined everywhere, oh, not defined, defined everywhere. And if we set y prime equal to 0, then we can find where it's equal to 0. So 0 equals 6 minus x squared. Let's multiply this by -1. 0 equals x squared plus x minus 6. Oh, that's much better. Why do I like that? Because now it's easier for me to factor. That's x, I just lost my train of thought. That's, that's x plus 3, x minus 2. There we go. And so it looks as though x is equal to -3 or +2. So here, now I'm going to use the second derivative test to find, so let's use second derivative test to determine if these points are maxes or mins. To determine, and in fact, to determine if we have max / min at critical points. I should mention, we cannot figure out exactly what these extrema might be because we don't have the original function, so we can't plug stuff in for y. We can't plug stuff in to find the y coordinate because I don't have the original function. But we can still determine if there is a max or min there. We just don't know exactly what the max or min is. So the way that we use the second derivative test, so plug x equals -3 into second derivative. Actually, let me write it this way. So y double prime of -3. Well, let me see. Y double prime of -3 is going to be -1 minus 2 times -3, or that's going to be -1 plus 6, and that is greater than 0. So this means, by the second derivative test, y has a local min at x equals -3. Okay, that's the second derivative test. Now let's do x equals, 2? 2. Y double prime of 2 equals -1 minus 2 times 2. So that's -1 minus 4, that's -5, which is smaller than 0. So this means y has local max at x equals 2. Okay, so we found where we have a local max and where we have a local min. We can't know exactly what they are because we don't have the original function, but we can still know that they are maxes and mins. Okay, so the next step, just like we did in the previous problem, is let's now find the inflection points. Let's find inflection points and investigate the concavity. So where is y double prime equal to 0 or undefined? Well, y double prime is -1 minus 2x. That's just a polynomial, so that's defined everywhere. So we just want to set that equal to 0. So defined everywhere. And then we have 0 equals -1 minus 2x. And so we solve for x, 2x equals -1, x equals -1/2. Okay? So to investigate concavity, I'm going to just make my number line, stick -1/2 in here, -1/2. Okay, and so I lost my train of thought. -1/2. Oh, we're going to plug in a point to the left and a point to the right. So let's look at, I don't know, y double prime of -1. Okay, well, y double prime of -1, it's going to be -1 minus 2 times -1. Excuse me. And that's going to be -1 plus 2, that's going to be +1, is greater than 0. So I'm concave up to the left of -1/2. And y double prime of, I'll plug in 0, well, that's -1, which is smaller than 0. And so I am concave down to the left of -1/2. So we have an inflection point at x equals -1/2. So let me look at my, let's go ahead and start to sketch our graph. Again, we only have so much information, but we can get the most out of that information. So the important x values I want to label are x equals -3, x equals 2, and x equals -1/2. So we have -3 here, throw -1/2 in there, and then that would mean that 2 is what, like here-ish, if we're trying our best to be to scale. So let's see, at -3 we have a max. Yeah, in fact, why don't we go ahead and even to help us, let's make our table again, because that would be helpful for me. So I'm going to label -3. I'm going to label -1/2. I'm going to label 2. Okay. And again, I want to know f prime, or let me write y prime. Is y prime increasing or decreasing? And what's the concavity looking like? Okay, so well, that connects to 3 there, -3. Now, we didn't actually go through and compute y prime at certain points. However, we can use the fact that we know that -3 is, let's see, -3 is a local min. So if we think about that visually, that means that the function is decreasing until it hits -3, and then it starts to increase. Okay, so that gives us that information. And then it increases until it gets to 2. And since x equals 2 is a local max, we know it's going to start to get smaller after x equals 2. In terms of concavity, we know that it's concave up everywhere to the left of -1/2. Up, up, and then down to the right of it. So now we can start to draw our picture. The function is decreasing and concave up until x equals -3. Okay, so it's decreasing, concave up, so that means something like this until x equals -3. At x equals -3, it's still concave up, but it starts to increase. Then we hit -1/2, and we start to flip to concave down, but we're still increasing. And then at x equals 2, we flip to decreasing, and we remain concave down. So our function might look something like this. Ta-da! Okay, so that does it for these 3 problems. I hope that you've seen how we're really combining a lot of information here, and we're able to deduce a lot about the picture of the function just from those pieces of information. In this last problem in particular, we didn't even have the function itself, but we were still able to sketch a decent graph. Yeah, I think that about does it. Again, we didn't get through a ton of